Hello everyone, I am Mansi Kiradu along with my group members to have our presentation on virtual memory and mapping techniques. Virtual memory. Here are the contents of our presentation. A technique using main memory as a cache. Consider a collection of programs is simultaneously running on a computer. The total time required memory is much larger than the amount of main memory. Main memory needs to contain only the active portions of the programs. The principle of locality applies. A program can only read and write the portions. Let us discuss few of the properties. Number 1, allows efficient and safe sharing of memory among multiple programs. Number 2, it removes the programming burdens of a small limited amount of main memory. Number 3, the programs sharing the memory change dynamically while the programs are running. The compiler sets each program into its own address space. Number 4, a VM block is called a page and a virtual memory miss is called a page fault. The operating system maps the virtual to any physical page. The page table plus PC plus registers specify the state of a program. To allow another program to use the processor, the state is saved. OS activates a process by loading the processor's state, including the PC. The OS needs to load only the page table register with the pointer to the table of the process to be run. Next. The OS allocates the physical memory and updates the page tables. Thank you. Now my group member will proceed.
Thank you, Mansi. Hello, everyone. My name is Anushka Ghosh. Now, I will tell you about the virtual cache. A memory addresses are translated to physical addresses before cache access, implying physical indexed and physically tagged, also called transparent cache. So there are some pros and cons. So the pros is that since the cache and the physical memory use the same names, so it can entirely be controlled by hardware, and the OS needs no interface. And the con is the address translation in is on critical path. Problem for high clock speed, large application data, larger TLB is needed. So virtual cache required address-based identifiers or the protection bits. Now, generally the cache is associated with each processor is accessed with the physical address opted up that the translation of virtual address in a translation look aside buffer, that is TLB. Now, since today's uniprocessors are very fast, it becomes increasingly difficult to include the TLB in the cache access path and still avoid wait state in the processor. The alternative is to access the cache with virtual addresses and to access the TLB on misses only. At heat, the time to access memory includes TLB and cache accesses. The two can be pipelined. So, can the TLB be eliminated from the critical path? So here we have to note one thing, that is the cache index involve both page offset and frame number bits, but the page bits are not transferred. So if each cache index if uses only page offset bits, TLB is eliminated from the critical path. There is also one con is that the cache index cannot grow. So the same cache and frame size. Cache capacity can grow only by increasing the block size and associativity. So physically index virtually tag eliminate the TLB. So here we see index is still cannot grow. Now, here this problem is solved by translating the TLB slice. As we previously said that the TLB is less expensive but on a critical path. So, in virtually indexed, virtually tagged translation, TLB is not needed anywhere. A TLB is stated on a cache miss. OS must translate the virtual address and load the data from the main memory. On a cache hit, the TLB is not on the critical path, hence it could be lost. So a word may be reached by two different programs, allowing one to write data without being aware of it. A compromise virtually indexed physically tagged cache. So this says that the tag extraction by cache indexing and tag translation of virtual addresses are done in parallel. Unlike physically indexed caches, management is still necessary because the cache is virtually indexed. Now, another member of our team will tell you about mapping.
Thank you, Anushka. Hello, everyone. I am Anushka Gupta and I will discuss about memory mapping. It is done when we transform data from main memory to cache memory, and it's also a mechanism that maps a portion of a file on disk to a range of addresses within an application address space. There are three types of mapping. They are associative mapping, direct mapping, set associative mapping. Now let us discuss the first type, associative mapping. The associative memory stores both address and data. The address value of 15 bits is 5-digit octal numbers and data is of 12 bits word in 4-digit octal number. A CPU address of 15 bits is placed in argument register and the associative memory is searched for matching address. Now let us see what is direct mapping. The CPU address of 15 bits is divided into two fields. In this, the 9 least significant bits constitute the index field and the remaining 6 bits constitute the tag field. The number of bits in index field is equal to the number of address bits required to access cache memory. Now I would like to hand over this presentation to our next member. Thank you.
Hello everyone, I am Aditi Gupta and now I will discuss about the set associative mapping. Set associative mapping is an improved version of direct mapping where the drawbacks of direct mapping is removed. The drawback of direct mapping is that two words with same index address but with different tag values can't reside in cache memory at the same time. This problem can be overcome by set associative mapping. In associative mapping, each word of a cache can't store two or more words of memory under the same index address, creating a set. Each data word is stored together with its tag, and the number of tag data items in one word forms a set. Set associative mapping combines direct mapping and associative mapping. In general, set associative mapping cache of set size k will accommodate k words of main memory in each word of cache. Now let's discuss an example of direct mapping to get a better concept. So you can pause the video and read the question. Here it is given that the memory unit is 64k into 16, and we know that main memory is divided into blocks and every block contains different number of words, and cache memory is divided into lines. So here main memory can store 64k word and each word is of 16 bit. Then from here we can calculate main memory size, which is 2 to the power 16 bits. As we can see that the power of 2 is 16, so number of address bit is 16. Since main memory word size is of 16 bits each, so data bits is 16 bits. Now it's given that cache memory size is 1k words. From here we get number of words. So 16-bit address is divided into tag and index. 1k words is equal to 2 to the power 10 words. So index is of 10 bits and tag is of 6 bits. Now it is also given that one block contains 4 words and we previously calculated total number of words in cache. So therefore we find total number of blocks, which is equal to total words in cache divided by number of words in each block. From here we get 2 to the power 8 blocks. Hence block is of 8 bits and number of words in one block is 4. So it is 2 square. Hence words is of 2 bits. Now let's talk about the pros and cons of mapping techniques. So first let's have a look at some of the advantages. So direct mapping is the simplest technique and mapping scheme is easy to implement. And in associative mapping, there is a flexibility when mapping a block to any line of the cache. Now let's have a look at some of the disadvantages of mapping techniques. So the drawback of direct mapping is that each block of main memory maps to a fixed location in the cache, and associative mapping is expensive as compared to random access memories. Plus it requires more space for tag field. So from here we conclude that set associative mapping combines direct mapping and associative mapping and utilizes the strength of both to reduce their drawbacks. That's all for our presentation. Thank you.